So we have our formulas for pseudocycles still on the blackboard, so I can be very explicit. So let's just do it if f is dynamical zeta function. So we have I over sigma that depends on beta, on this dual parameter to our observable, and then it depends on S, but through beta, if you wish, because we'll be interested in leading zero, this particular curve. And now what are these partial derivatives? So if I take dd beta of just partial, the only dependence on beta is in AP. So it'll get down sum minus, this goes away in the partial, minus 1 k plus 1, and then pi, where this is the number of terms in a product of pi, and this brings down a to the pi. And then we set, after we take the derivative, it takes s equal to 0, beta equals to 0, so this exponent goes away. And I find out that this is our average quantity compute on all pseudocycles weighted by the stability of the pseudocycle. And DDS of the same quantity, because the time shows as a minus sign here, this becomes plus sum over all pseudocycles minus 1 k plus 1, and then derivative brings down the period. And this is why I call these things expectation value of A. So it's a computed on all configurations, weighted by the cycle expansion for zeta function in this case. So I'll call this zeta. And this is expectation value of mean time you get someplace, computed by sigma. So for binary example, we know this cycle expansion, so we can just write them down. Compute your observable on a fixed point, a fixed point 0, divide by stability of the fixed point, plus compute it on the other fixed point, divided by lambda 1 stability of that fixed point, plus computed on the 2 cycle, divided by the 2 cycle, minus, now remember these guys add in pseudocycles, minus computed on one cycle, fixed point computed on the other fixed point, and multiplied by the weight of each one of them. Plus, same thing for 3 cycles. And our expectation, our observable A, is the ratio of these two sums. So you have a sum here which starts with shortest cycles, which are least unstable, so I get the largest contribution from them. Then I add to this the correction from the 2 cycle, and this goes on, divided by time of the first period. So if this is a Poincaré section, there will be non-trivial return map. Time of the other one, also non-trivial return map. If it's discrete map, this will be just once, plus correction, and computing the time of 2 cycle minus estimating it by just as a sum of the 2 fixed point return times. This one divided by the 2 cycle, and the correction being weights of individual periodic orbits. The main thing to notice about the cycle formulas for dynamical averages that they have the same structure as the cycle formulas for expansion of zeta function of Fredholm determinant. They're dominated by short periodic orbits because these lambdas are typically, let's say, of order 2 each. And the value of your observable in the neighborhood of the fixed point. But then there is a correction in which you compute your observable by integrating it over the cycle. This is longer, so it's exponentially more unstable. So if this was 2, this would be of order 4, let's say. But then it's shadowed by your estimates of what observable would have been on each periodic orbit. So we again have shadowing. If the original expansion for periodic orbits was converging, this is going to converge as well. I won't do very much more on this. I suggest you read the book.